Alright, the purpose of this video is to walk us through practicing the quotient rule. Once again, it's a shortcut for finding the derivative of a function. It's complicated, but not nearly as complicated as having to do this using the first principles. So remember, whenever we see a function where there's a variable expression in a numerator and a variable expression in a denominator, then we would say this is a candidate for the quotient rule. So if you're going to divide one function by another and you want to take the derivative or find the rate of change of this function, quotient function, then we follow this particular pattern. You take the upper function and the lower function and you define them separately, and then basically following this acronym, ho for the lower function, d for the derivative, high for the upper function. So it's ho d high minus high, the upper function, times the derivative of the lower function, high d ho, over ho ho. So this is 1 minus x squared, so that's showing the second function, or the bottom function, the lower function, is multiplied by itself twice. So from there, we can do some, we have to take the derivative. So right here I'm going to take the derivative of x to the 1/2. So keep the 1 minus x, and the, derivative of x to the 1/2 is we multiply 1 by 1/2, and then we drop the power by 1. That's where the negative 1/2 comes from. And then we keep the x to the 1/2 and take the derivative of 1 minus x. The derivative of 1 minus x is in fact negative 1. Remember, this is a linear function. The slope of a linear function with a slope of negative 1 is negative 1. So put that, don't forget the ho-ho. And now all I'm going to do is distribute this half x to the negative half into the 1 minus x, so that's here and here. And then I'm going to take the opposite of negative x to the 1/2, which gives me a positive x to the 1/2. Notice, by the way, when I multiply 1/2 x to the negative 1/2 times 1, it's just itself. When I multiply 1/2 x to the negative 1/2 times x to the 1, we're going to have minus x to the 1/2, because 1 plus negative 1/2 equals 1/2. In other words, when you multiply numbers of the same base, add the exponent. So that's where that 1/2 came from. Now we're going to collect like terms. Here's x to the 1/2, here's a negative half x to the 1/2. They combine to give us positive x, 1/2 x to the 1/2, and that's over ho-ho. And then all we have to do now is find a term that has the lowest power. So this is x to the negative 1/2, this is x to the 1/2. X to the negative 1/2 is the lowest, plus there's also a common factor of 1/2. So I'm going to take out the 1/2 and the x to the negative 1/2 as a factoring. So notice what I did then is we took out the entire first term, leaving us with a 1 factor left over. And here we're going to take x to the 1/2 divided by x to the negative 1/2. There we subtract the exponents, which is why we get x to the 1 power. Put that over ho-ho. And the only other thing we have to deal with is this 2 is a denominator, so we'll bump it down to the denominator. And x to the negative 1/2 is really 1 over square root of x. So that's going to lead to a final function that looks just like this one. Now, just to make sure, you can see what I have is a graph over here, and the red represents the original function, and it seems to be that the function is increasing all the time, so we're always going to have positive tangent slopes. What the derivative is saying is, well, it's always positive. Since the function's always increasing, f of x should always be positive. And anytime x is bigger than 0, this is in fact always going to be a positive numerator. A squared and a square root in the denominator, that's always positive as well. So I'm inclined to believe that this is correct. But I could actually enter in this equation into Desmos, and here is Desmos's calculator-derived derivative, and this is my derivative. And so I'm comparing the blue against the green, and you can see the blue was overshadowed or covered up by the green. Therefore, I did in fact find the correct derivative. Thanks for watching.